Alright, okay. So this is question 11 on the practice test on Canvas that he gave us. So for question 11, they're going to give us a structure like this. So when they say how many signals would be observed in the 13C NMR, so what we do is that we're looking at how unique the carbons are. So we can start from the chain right here. So we know that this carbon right here is unique because it has a carbonyl or an aldehyde, carbonyl and hydrogen, whereas this one, for example, doesn't. So this one is definitely different than this one. So this one is different than this one because this C is bound with another carbon with an aldehyde. So this is different than, it sounds confusing, but it helps if you look at this one individually and see what its neighboring like carbons and what they're binding with. So this one is different because it has a double bond and a single bond. And this one is different than this one because it does have a double bond, but also it's bound with this ring carbon in a ring. Then when we look at the ring, so now let's count this 1, 2, 3, 4, 5. So now looking at the ring, we can draw a symmetry right here, and then this carbon with this carbon is the same, so we would count this as 1. And this carbon right here with this carbon, we can count this as 1. So 1, 2, 3, 4, 5, 6, 7, and then this carbon right here is different. So this is 8, and this carbon right here is a methyl, so we can count this as 9. So this is where we get the 9 from. Now for B, now we want to know the greater than 100 ppm would be observed at the 13 CNMR. So where we get that basically, oh my god, here it comes. Okay, so we get that from the page 657 and 1420 section, and we get it from this table and this table. So this is actually for a different thing, but we can look at this. So we look at where the 100 ppm is at, and it looks like it's for the carbon double bond. So that's where we get that from. So we know we should count the double bonds because we know that it's 100 ppm gives us the double bond. So let's go back to where we were. So now what we do is that we look at this carbon. So that's 1. So we're going to put this sign on it. So that's 1. And these two carbons have a double bond. So this is 2, 3. This carbon has a double bond. So 1, 2, 3, 4. So now we look at the symmetry as well. So this is 5, 6, and then 7, because we count these as 1. So 1, 2, 3, or 1, 1, 2, 3, 4, 5, 6, and 7. So that's where we get the 7. Okay, now for C, how many total signals 13C det 135 NMR would be observed? So now what helps with that, as we talked about earlier, that CH2 means di, which means 2. So it's, di means down, sorry.
Like 6 feet under.
Yeah. And the CH and CH3 would give us up. So now what they're looking for, where are the CH and CH3 and CH2. So let me erase this. I'll just pause for a little bit, and then I'll erase it so we can see it clearly. So this is 1, 2, 3, and 4. This has nothing, so just a C. 1, 2, 3. This is a CH because it has an H, so this is 2. So we do the symmetry again, so this will be 1, and this CH, so this is 3. And then this one right here, it's 1, 2, 3, 4, so it does not have any hydrogen, so we don't look at this one. This one right here, 1, 2, 3, and an H, so this is CH, so this is 4. This one right here, it's the same. 1, 2, 3, CH, this is a 5. 1, 2, this is a CH2. This is a 6, and this one right here, oh wait, and we're forgetting this.
Yeah.
CH. So this is going to be 7. So that's where we get the 7. And lastly, for D, how many signals will be inverted? Inverted means down. And we know down is CH2. So when we look at this right here, we know that only the CH2 that we have is the one right here. So this is where we get 1 from.
Woo!